A silent titan sleeps at the center of our galaxy, and it controls everything. These supermassive black holes are not just empty voids, but cosmic regulators with a firm grip on the life and death of galaxies. By the end of this, you will understand the invisible forces that dictate the growth of every major galaxy in the universe. How does a black hole's explosive outburst reach across thousands of light years to shut down star formation? What keeps our own Milky Way from devouring itself in a frenzy of new stars? The answers reveal a universe far more interconnected than we ever dreamed. What does it mean that our entire cosmic neighborhood is held in balance by such a dark and powerful heart? Think of a place where the universe itself breaks down. A supermassive black hole is not merely a hole, but a cosmic object of almost incomprehensible power. At its heart lies a singularity, a point where matter is crushed to infinite density, warping the fabric of space and time around it into a prison from which nothing, not even light, can ever return. This ultimate point of no return is marked by the event horizon, a shadowy boundary that forever separates the inside of the black hole from the rest of the universe. What makes these objects supermassive is their staggering scale, containing the equivalent mass of millions, even billions, of suns all compressed into a region that could fit within our solar system. Nearly every large galaxy we see, including our own Milky Way, has one of these gravitational giants sleeping at its core. Our local titan is known as Sagittarius, a star, a relatively quiet beast with about 4 million times the mass of our Sun. But how did such monsters come to be? Their origins are a profound mystery. Some may have started as smaller, star-sized black holes that gorged on gas and dust for billions of years. Others might have been born in the chaotic infancy of the cosmos, forming directly from the collapse of immense primordial gas clouds. Once established, their character is defined by two key properties: their spin and how quickly they consume or accrete surrounding material. A rapidly spinning black hole drags the very fabric of space around with it, storing unimaginable rotational energy. Its accretion rate, whether it is fasting or feasting, dictates its activity. It is these fundamental traits that transform a black hole from a passive trap into an active galactic architect, a central regulator with the power to nurture or strangle the galaxy it calls home. That brilliant light show is far from a gentle glow. As gas and dust spiral inward at ferocious speeds, friction and magnetic forces heat this material to millions of degrees, creating a maelstrom of incandescent plasma. This is the accretion disk, a cosmic engine of staggering power. Its brilliance is a direct conversion of gravity into light, a release of energy so potent it can outshine every single star in its host galaxy for millions of years. We call these blazing cores active galactic nuclei, or a GN, and they are the universe's ultimate lighthouses. But this energy is not merely light. It floods the galaxy with a torrent of radiation, from searing X-rays to powerful radio waves. Think of a vast cloud of cold hydrogen gas, the raw material for new stars, drifting peacefully in the galactic suburbs. When the blast of radiation from the central black hole hits this cloud, it does not just illuminate it. The energy violently heats the gas like a blowtorch applied to a snowbank. The individual gas particles are energized, bouncing away from each other with too much force to ever collapse under their own gravity. That crucial, quiet process of star formation is shut down completely. The black hole, through the sheer power of its feast, has put a definitive brake on the growth of its own galaxy. This is the first and most direct way it asserts control, by holding the very building blocks of stars hostage. But the story does not end with a flash of light. This released energy can also take a far more physical and violent form. This is where the black hole's power becomes truly physical. From the very poles of this spinning monster, twin beams of incandescent plasma erupt, moving at almost the speed of light. These are relativistic jets, cosmic fire hoses that blast across the galaxy and far out into the emptiness of intergalactic space. They are born from chaos, launched when the intensely twisted magnetic fields within the accretion disk channel some of the inflowing matter and fling it outward with unimaginable force. These jets carry away a staggering amount of the black hole's energy, acting as a release valve for the system, but their journey is where the real impact begins. When one of these focused beams smashes into a calm cloud of interstellar gas, the effect is anything but gentle. It carves out colossal bubbles in the galactic medium and sends powerful shockwaves rippling through the cosmos. The energy of the impact violently heats the surrounding gas, preventing it from cooling and collapsing into new stars. In rare, almost paradoxical moments, the shockwave from a jet can squeeze a gas cloud just enough to trigger a burst of star formation, a fleeting act of creation. Yet far more often, the jet's role is one of pure destruction, simply blowing the star-forming material away entirely, clearing out the galactic nursery. This is the black hole's dual nature in its most dramatic form, a creator and a destroyer whose influence stretches thousands of light years from its dark heart, sculpting the galaxy on a truly monumental scale. This radiative onslaught is the black hole's third and most pervasive instrument of control. While the jets are focused beams of destruction, the radiation from an active black hole floods the entire galactic system, a silent, invisible tide of energy. Every active supermassive black hole emits a torrent of high-energy photons, the fundamental particles of light, which pour out in all directions. Think of a cold, dark cloud of hydrogen gas drifting through a spiral arm. This cloud is a potential stellar nursery, a place where gravity could slowly pull the gas together until a new star ignites. But when the black hole's radiation washes over it, the effect is transformative. These high-energy photons smash into the gas atoms, stripping away their electrons in a process called ionization. This act of ionization violently heats the gas, causing its pressure to skyrocket. The cloud is no longer a calm, collapsing entity. It becomes a hot, turbulent, and expanding bubble, its particles buzzing with too much energy to ever come together. This is radiative feedback, a cosmic thermostat at work. The black hole senses, in a way, the abundant fuel for star formation and responds by turning up the heat, preventing the galaxy from burning through its gas too quickly in a runaway explosion of new stars. We see this principle in action when we observe quasars, the most intensely luminous black holes in the universe. The regions of space surrounding these brilliant beacons are often strangely quiet, with star formation rates far lower than we would expect. The evidence is clear: the black hole's radiant energy has effectively sterilized its immediate environment, putting a ceiling on galactic growth. But what happens when even this pervasive heating is not enough to maintain the balance? The black hole has one final, more explosive option. Sometimes the black hole's response is not a focused beam or a silent wave, but a storm. When radiation and particle pressure from the active core build to a critical point, they can trigger hurricane-force winds that blast out from the galactic center. These are galactic outflows, colossal rivers of superheated gas streaming outward at thousands of kilometers per second. They carry a staggering amount of the galaxy's own star-forming material, hurling it high above the galactic disk into the halo, or even casting it out into the void of intergalactic space. This is the most direct form of black hole intervention. By forcibly ejecting the cold hydrogen gas that fuels star birth, these winds starve the galaxy of its future. The galactic nursery is not just put on hold, it is actively dismantled, its building blocks thrown out into the cold. Sophisticated computer models of galaxy evolution reveal a clear truth. Without this powerful quenching mechanism, galaxies would gorge on their own gas, igniting stars in a frantic, unsustainable burst. They would burn too bright and die too young, becoming monstrously oversized before collapsing into chaos. The supermassive black hole, through these epic winds, acts as a cosmic regulator. It is not merely a destructive force, but a stabilizing one, capable of large-scale environmental engineering that shapes the destiny of its entire home. This reveals a profound and unexpected balance, a feedback loop of cosmic proportions. This cosmic tug-of-war leaves behind a permanent signature, a hidden pattern written into the fabric of galaxies themselves. For decades, astronomers noticed something strange, a pattern so consistent it could not be a coincidence. The mass of a galaxy's central bulge, that dense swarm of ancient stars at its core, is locked in a tight relationship with the mass of its supermassive black hole. A larger bulge always means a more massive black hole. This is the M-sigma relation, a fundamental rule of cosmic architecture. The correlation is astonishingly precise. It is as if every time a galaxy added a certain amount of mass to its central hub, its black hole was instructed to grow by a corresponding amount. This is not a random partnership. It points directly to a shared history of growth, a co-evolution spanning billions of years. The feedback processes we have explored are the missing link in this relationship. They are the communication channel that keeps the black hole and the galaxy in lockstep. Imagine a galaxy growing through cosmic mergers, pulling in vast rivers of fresh gas. This bounty feeds the black hole, igniting its active phase. The resulting outburst, whether through radiation, jets, or winds, then heats and expels the surrounding gas. This does two things simultaneously. It stifles the formation of new stars in the bulge, and it cuts off the black hole's own food supply, forcing it into a dormant state. The black hole's activity directly regulates the growth of its galactic home, while the galaxy's growth dictates when the black hole gets to feast. They are bound in a symbiotic dance, a feedback loop of creation and restraint. This reveals that the supermassive black hole is not a passive occupant or a silent destroyer. It is a central governor, an integral component hardwired into the galaxy's development from the very beginning. Its gravitational might acts as the control dial for the entire system, ensuring that growth is orderly and sustainable. To see how this delicate balance was first struck, we must journey back to the dawn of time, to the chaotic infancy of the cosmos. A supermassive black hole grows through a cycle of fasting and feasting. Its primary meal is the gas that permeates the galaxy, drawn inward by its overwhelming gravity. As this gas spirals into the accretion disk, it is converted into immense energy, powering the active galactic nucleus. But sometimes the black hole consumes something more dramatic. When a star wanders too close, the black hole's tidal forces can stretch and tear it apart in a spectacular event known as a tidal disruption. The star is shredded into a stream of incandescent debris, much of which is devoured, providing a sudden, brilliant feast. Yet these stellar snacks are rare. The most significant growth spurts occur during cosmic collisions when two galaxies merge. The chaotic gravitational dance of a merger funnels enormous reservoirs of gas directly toward the central black hole, like rivers of fuel flowing into a dormant engine. This triggers an eruption of activity, turning the core into a brilliant quasar that can dominate the combined galaxy's light. This growth is not steady. It happens in violent, intermittent bursts separated by long epochs of silence. the black hole may slumber for hundreds of millions of years, then awaken in a fiery outburst that reshapes its entire galaxy before its fuel supply is once again cut off. This episodic nature is the key to its regulatory role. The black hole is only active when there is an overabundance of gas, precisely when the galaxy is at risk of growing too fast. Its most powerful feedback, the winds and radiation that quench star formation, is deployed only during these critical feasting periods. It is a dynamic, self-correcting system, a cycle of feeding and feedback that has sculpted galactic ecosystems for billions of years. This quenching process solves one of the universe's great mysteries, the existence of red and dead galaxies. Across the cosmos, we find immense elliptical galaxies that are cosmic graveyards, filled with ancient red stars and almost no young blue ones. They have ceased forming new stars, and for a long time we did not know why. Their vast reservoirs of hydrogen gas are not gone, they are still present, but they are searingly hot, a diffuse and turbulent fog that cannot collapse. The black hole's feedback is the invisible hand that turned off the star-forming tap. It is the reason these galaxies are not still blazing with stellar nurseries. Without this regulatory break, a massive galaxy would continue to devour its own gas in a frenzy of star formation. It would become a monstrously bloated and unstable system, burning through its fuel in a relatively short cosmic time before fading into an irregular, chaotic state. The demographics of the universe would look entirely different. Instead of the orderly distribution of galaxy types and sizes we observe, we would see a cosmos dominated by these overgrown, frantic giants. The black hole's ability to quench is not a minor side effect. It is a core ingredient written into every successful theoretical model of how galaxies evolve. It is the fundamental suppression mechanism that explains why our universe looks the way it does. But how do we move from theory to certainty? The proof is etched across the sky in the silent testimony of galaxies themselves. The proof is etched across the sky in silent testimony written in X-rays and radio waves. We no longer need to imagine black hole feedback. We can see its fingerprints directly. The Chandra X-ray Observatory has peered deep into the hearts of galaxy clusters, revealing breathtaking structures. Enormous cavities, each large enough to swallow thousands of solar systems, are carved into the searing hot gas that permeates these clusters. These are not random voids. They line up perfectly with the relativistic jets erupting from the central galaxy's supermassive black hole, like cosmic bubbles blown into a hot liquid. The jets have literally pushed the gas aside, creating vast, empty spaces that slowly rise through the cluster, their edges marked by faint ripples of compressed material. This is feedback captured in a single, stunning image, a fossil record of a black hole's powerful outburst that occurred millions of years ago. But the evidence does not stop with these silent sculptures. When astronomers point spectroscopic instruments at distant quasars, they detect something equally telling: the Doppler shift of light from colossal winds. We see gas that is racing away from the galactic center at thousands of kilometers per second, a direct observation of the very outflows that theory predicted. The chemical signature of this fleeing material matches the gas clouds that would normally form stars, confirming that the black hole is actively expelling the galaxy's future building blocks. Perhaps the most compelling clue is a pattern of cosmic opposites. In system after system, a clear anti-correlation emerges. When the luminosity of the active galactic nucleus is at its peak, blazing with intense light, the measured rate of star formation in that same galaxy plummets. It is as if a switch has been thrown. The black hole turns on and the stellar nurseries are shut down. This relationship, seen across multiple wavelengths of light from Hubble's optical images to ALMA radio waves observing cold dust, transforms an elegant theory into an observed physical law. The case is closed. Black holes do not merely reside in galaxies, they govern them. This wealth of data from our greatest observatories confirms a cosmic dialogue, a conversation of push and pull that has been ongoing since the universe was young. But this entire cosmic drama plays out upon a hidden stage, wrapping around every galaxy from the smallest dwarf to the largest elliptical, is a vast and invisible sphere of dark matter. This mysterious substance, which does not emit or absorb light, forms a gravitational scaffold, a deep well of unseen mass that holds the entire visible galaxy within its grasp. It is this dark matter halo that first draws in the ordinary gas, the baryonic matter, which will eventually form stars and feed the central black hole. The halo's immense gravity acts as a cosmic anchor, dictating how quickly and efficiently gas can flow into the galactic core. In the most massive halos, the gravitational well is so deep and powerful that it can trap even the superheated gas blasted out by the black hole's own outburst. This creates a profound loop. The black hole heats the gas to prevent star formation, and the dark matter halo's gravity holds that hot gas in place, preventing it from escaping entirely. This ensures the feedback is not a one-time event, but a lasting, regulatory presence that can maintain the galaxy's quiescent state for billions of years. The interplay between the invisible dynamics of dark matter and the violent, visible processes of black hole feedback is one of the most critical frontiers in understanding galaxy formation. It reminds us that the story is not just about the brilliant black hole and the shining stars, but also about the unseen gravitational hand that guides them both. This hidden connection places the life cycle of a single galaxy within the grand architecture of the cosmic web itself, a vast network of dark matter filaments along which galaxies form and evolve. To truly isolate the black hole's role, we must build a universe from scratch. Inside the world's most powerful supercomputers, physicists construct entire digital cosmos, governed by the unbreakable laws of gravity, radiation, and fluid dynamics. These are not simple animations but fully realized virtual realms, where billions of particles representing dark matter, gas, and stars interact over billions of simulated years. Projects like Illustris TNG and EAGLE are at the forefront, creating vast, evolving galactic ecosystems. Their most critical ingredient is the precise coding of active galactic nucleus feedback. When researchers run these simulations without this key mechanism, the result is a universe that looks nothing like our own. The simulated galaxies gulp down their gas, spawning stars in a frantic, unsustainable frenzy. They grow monstrously large, their central bulges bloated with young stars, completely failing to match the quiet, mature galaxies we actually observe through our telescopes. The discrepancy is a glaring failure, but when the code is updated to include the black hole's regulating power, everything changes. The virtual galaxies begin to look right. Their growth is tempered, their star formation rates decline realistically, and they settle into the same diverse population of spiral and elliptical shapes we see in the night sky. These digital experiments allow scientists to play with cosmic variables, tweaking the strength and timing of black hole outbursts to see the precise consequences. They can watch as a simulated quasar erupts, its winds blowing a galaxy's gas reservoir into a hot, diffuse halo, effectively quenching star formation for eons. The success of these models in mirroring reality provides some of the strongest computational proof we have. It confirms that the supermassive black hole is not a minor character in the galactic story, but a central author, its violent feedback etched into the very blueprint of every major galaxy. These virtual laboratories are now guiding our gaze, pointing telescopes toward new cosmic relationships and pushing us closer to a complete theory of galactic life and death. The infant cosmos was a place of both brilliant creation and violent regulation. Within the first billion years after the Big Bang, the universe witnessed the birth of its first supermassive black holes, colossal entities that grew with astonishing speed. We know this because we can see their light, the brilliant glare of quasars so distant their light has been traveling for over 13 billion years. The existence of these quasars is a profound puzzle. They reveal black holes already weighing 1 billion solar masses when the universe was less than 1/10 of its current age. How could such monsters form so quickly? This rapid growth suggests a primordial feeding frenzy, a time when gas flowed into these dark hearts unimpeded, fueling outbursts of unimaginable power. In these dense, chaotic environments, black hole feedback was not a subtle regulator, it was a foundational force. The outbursts from these early quasars were likely far more violent and concentrated than anything seen in the modern universe. Their intense radiation and powerful winds did not just shape their host galaxies, they blasted the raw material of star formation far and wide, seeding the pristine intergalactic medium with the first heavy elements forged in their accretion disks. This enrichment polluted the cosmic waters, changing the very chemistry of the universe and setting the stage for future generations of stars and planets. Perhaps their most critical role was in ending the cosmic dark ages. The searing light from these earliest quasars contributed to the epoch of reionization, ripping electrons from atoms of neutral hydrogen that filled all of space. This process burned away the primordial fog, gradually clearing the universe and making it transparent to light for the first time. By studying these most ancient systems, we are looking at the very first experiments in black hole galaxy co-evolution. They represent the initial conditions, the raw, unfiltered version of the feedback loop we see in a more refined form today. The violence of the early cosmos established the rules that would govern galactic growth for billions of years to come, a legacy written in light across the expanding universe. This cosmic dialogue between black holes and their galaxies has produced two dominant archetypes, the serene ellipticals and the vibrant spirals. The story of how a supermassive black hole controls its home is written in the stark differences between them. Elliptical galaxies are the quiet elders of the cosmos, vast spheres of ancient red stars. They typically harbor the most massive black holes of all, relative to their size. These titans have already done their most important work, having unleashed powerful feedback long ago that effectively sterilized the galaxy. The evidence is overwhelming. The hot, diffuse gas that remains cannot cool and collapse, and star formation has been almost completely quenched. These galaxies are often found in dense clusters, environments where galactic mergers were frequent in the past. It is these violent collisions that likely funneled immense amounts of gas to the central black hole, triggering the cataclysmic outbursts that blew away the star-forming fuel and left behind the calm, red giant we see today. In contrast, spiral galaxies like our own Milky Way are the cosmic nurseries, their beautiful arms alive with the blue glow of young stars. Their central black holes are often less massive and currently quiet. Here, feedback is a more gentle and continuous process, a subtle regulation rather than a violent shutdown. Occasional, moderate outbursts may heat gas just enough to prevent runaway star formation without fully suppressing it, maintaining the delicate balance that allows for a steady, sustainable rate of new stars. The key that determines a galaxy's fate is its history of violence. A major merger between two spiral galaxies can be a transformative event. The chaotic gravitational dance funnels a tsunami of gas toward both black holes, igniting them as brilliant quasars. The resulting feedback is so intense it can blow away nearly all the cold gas, permanently halting star formation in the disk and transforming the entire structure into a smooth, featureless elliptical. This diversity reveals a crucial truth. Black hole feedback is not a single, uniform force. It is a versatile tool whose strength and impact are exquisitely tuned by the galaxy's own environment and life story. The quiet heart of our own spiral Milky Way and the dormant giant in a distant elliptical were both shaped by the same fundamental process, yet their present states tell vastly different tales of cosmic history. This understanding of galactic types brings the entire cosmic mystery closer to home, raising a profound question about our own place in this grand cycle. Our own galactic center holds a sleeping giant named Sagittarius, a star. This supermassive black hole, with a mass of about 4 million suns, is remarkably calm, a quiet neighbor compared to the blazing monsters seen in other galaxies. Its current state is one of fasting, with only a trickle of gas and dust spiraling into its accretion disk. This low accretion rate means it emits very little radiation or powerful jets, exerting minimal feedback on the Milky Way around it. This gentle state is a gift to our galaxy. It allows vast clouds of cold hydrogen gas in the spiral arms to remain undisturbed, quietly collapsing under their own gravity to birth new generations of stars. The vibrant stellar nurseries we see, like the Orion Nebula, are a direct consequence of our black hole's present tranquility, but this piece is only a chapter in a much longer story. Looking above and below the galactic plane, the Fermi Gamma Ray Space Telescope has revealed a startling truth. Towering structures known as the Fermi bubbles stretch for tens of thousands of light years, glowing with high-energy gamma rays. These colossal bubbles are a fossil record, the ghostly aftermath of a past eruption. They suggest that Sagittarius, a star, was not always so quiet. Millions of years ago, it likely experienced a significant feeding event, launching powerful jets or outflows that inflated these gigantic structures and heated the galactic halo. This evidence transforms our local black hole into a unique cosmic laboratory. Its proximity allows us to study the physics of accretion and feedback in exquisite detail, observing the calm after the storm. Its quiescent state is a powerful reminder that black hole activity is episodic, a cycle of long slumbers punctuated by brief, violent outbursts. Our galaxy, and our place within it, exists in one of those calm periods, a temporary peace in the ongoing dialogue between a black hole and its home. This on and off nature of black hole activity is a crucial piece of the puzzle. An active galactic nucleus is not a steady beacon but a cosmic strobe light, flickering on and off over timescales that range from a few years to many millions. The trigger is brutally simple: the availability of fuel. When a fresh river of gas is funneled toward the center, the black hole awakens, igniting its accretion disk and launching its powerful feedback. But this very outburst, the radiation and the winds, heats and expels the surrounding gas reservoir. In doing so, it ultimately starves itself, cutting off the food supply and forcing a return to quiescence. The brilliant quasar fades back into a dark, silent heart. This creates a dynamic and self-regulating cycle. During the intense but brief active phases, the black hole exerts its full control, quenching star formation across vast stretches of the galaxy. But then, during the long eons of silence that follow, the galaxy gets a reprieve. If any cold gas remains or new gas drifts in, star formation can slowly, tentatively resume. It is this intermittent pulsing that prevents a single, catastrophic outcome. Without these cycles, a galaxy could either be permanently sterilized by a constant blaze of radiation or spiral out of control in a frenzy of unchecked stellar birth. The black hole's activity comes in powerful corrective bursts, a regulatory hand that only slams down when absolutely necessary. This variability means that to understand a galaxy's true history, we must look beyond its current state. A quiet galaxy like our own Milky Way may be between outbursts, while a brilliantly active one is in the throes of a transformative event. Astronomers study these different states to piece together the duty cycle of feedback, calculating how often and for how long a typical black hole is active over billions of years. It is the sum total of these on and off periods, the integrated effect of all the outbursts, that ultimately sculpts a galaxy's final form. This reveals that timing is everything in cosmic regulation. The exact sequence of a galaxy's feeding and feedback cycles, a rhythm set by the flow of intergalactic gas and the chaos of mergers, writes its unique destiny. Yet behind the blinding light of the accretion disk and the fury of the jets, there operates an invisible architect. The true power to channel and direct this cosmic storm belongs to magnetic fields. These are not the simple fields of a bar magnet, but dynamic, living structures woven through the superheated plasma. As the accretion disk whirls around the black hole at fantastic speeds, its inner regions orbit much faster than its outer edges. This differential rotation acts like a cosmic dynamo, stretching and winding the magnetic field lines, amplifying their strength to almost unimaginable levels. This process performs a critical sleight of hand. The twisted magnetic fields act like a cosmic brake, grabbing onto the fast-spinning inner material and effectively flinging its rotational momentum outward. This allows the gas to lose energy and spiral inexorably inward toward its doom. Without this magnetic transport of angular momentum, matter would simply orbit forever, never feeding the black hole and never powering the brilliant display. But the magnetic field's most spectacular feat occurs in the black hole's ergosphere, a region just outside the event horizon where space itself is dragged around the spinning monster. Here, the field lines are not just wound up, they are spun into a rigid, rotating structure like a cosmic slingshot. This configuration acts as a colossal particle accelerator, funneling and flinging ionized plasma along the black hole's spin axis, launching it outward at nearly the speed of light. These are the relativistic jets we observe tearing across galactic space. The precise shape and power of these jets, whether they are tightly focused or wide and diffuse, are dictated entirely by the geometry and strength of the magnetic field anchored near the event horizon. This invisible machinery is what ultimately harnesses the raw gravitational energy of the black hole, converting it into a directed galactic-scale outburst. The entire science of magnetohydrodynamics, which studies how magnetic fields and electrically conducting fluids interact, is essential to modeling this incredible transformation. It explains how a dark, silent heart can build the very tools that let it reach across thousands of light years to sculpt its home. This magnetic mediation is the final, crucial piece that explains why some active galaxies show brilliant, pencil-thin jets while others blaze with a more diffuse radiance, a diversity of phenomena all born from the same dark heart. These ripples in the fabric of spacetime are a new language for the cosmos. When the LIGO and Virgo observatories first detected gravitational waves, they did more than confirm a century-old prediction. They opened a silent channel to the universe's most violent events. The gentle stretching and squeezing of space itself, caused by the collision of two stellar mass black holes, was captured for the first time. But this was only the beginning of a new sense. For supermassive black holes, the story is even more profound. When two galaxies collide and merge, their central giants are destined to meet. Drawn together by gravity, they begin a slow cosmic waltz, orbiting each other for millions of years. As they spiral inward, they churn the fabric of spacetime, sending out relentless, low-frequency gravitational waves that ripple across the universe. The final act of this dance is a coalescence, a violent merger that releases more energy than all the stars in the observable universe combined, all emitted not as light, but as a final, thunderous burst of gravitational radiation. The aftermath of such a collision can be chaotic. The recoil from this asymmetrical blast of energy can be so powerful it literally kicks the newly formed, supermassive black hole clear out of its galactic center. Imagine the regulator of a galaxy, the very heart of its feedback cycle, suddenly ejected into the dark intergalactic void. This event could permanently disrupt the delicate balance we have explored, leaving a galaxy without its central governor, its future growth unchecked. The study of these supermassive binaries is still in its infancy, but it holds the key to a galactic family tree. The gravitational wave signal from such a merger encodes the masses and spins of the original black holes, a direct record of a galactic collision that occurred billions of years ago. By listening for these signals, we can piece together the merger history of the universe itself, understanding how galaxies assembled over cosmic time. While our current ground-based detectors are tuned to the high-frequency chirps of stellar mass black holes, the low, rumbling waves from supermassive binaries require a different kind of observatory. Future missions like the Space-Based Laser Interferometer Space Antenna, or LISA, will open this low-frequency window. By placing 3 spacecraft millions of kilometers apart, LISA will form a gravitational wave telescope of staggering precision, capable of hearing the universe's deepest hum. This new sense of hearing complements our sense of sight. Electromagnetic observations show us the light from black hole accretion and feedback, while gravitational waves bring us the direct story of their motions and collisions. Together, they provide a holistic, multi-messenger view of black hole dynamics, revealing a universe that speaks to us through both light and gravity. Every ripple in spacetime carries a message from a cataclysm of unimaginable scale, enriching our understanding of how these dark hearts form, evolve, and ultimately shape everything around them. Every single cloud of gas in a galaxy faces a cosmic crossroads. Its future hangs in the delicate balance between two opposing forces, an inward pull toward creation and an outward push toward oblivion. On one hand, gravity relentlessly coaxes the gas to cool, to condense, and to collapse under its own weight. If this process goes unchecked, the cloud will ignite into a brilliant new star, adding its light to the galactic disk. This is the path of growth, but there is another, more violent destiny. When the central black hole erupts into activity, it floods the galaxy with energy that violently heats the gas. The individual atoms are sent buzzing with such ferocious motion that they can no longer cling together. The cloud does not collapse, it expands and dissipates, its potential for star formation erased in a flash of heat. In the most extreme cases, this gas is not just heated, it is physically hurled out of the galaxy entirely, cast into the dark intergalactic void, lost forever to its home. The fate of this gas, whether it becomes a star or is banished into nothingness, is the single most important factor determining a galaxy's growth. Without the black hole's intervention, this cycle would spiral out of control. Imagine a massive galaxy sitting within a deep well of dark matter gravity. Its powerful pull would draw in colossal amounts of cold gas. This gas would cool with breathtaking efficiency, collapsing into a frantic, runaway explosion of new stars. The galaxy would gorge itself, becoming monstrously oversized, burning through its entire fuel reserve in a relatively short cosmic time. We simply do not see these overgrown behemoths in our universe, and the reason is the supermassive black hole. It acts as a cosmic arbitrator, a balancing force that injects just enough energy into the system to prevent this catastrophic cooling. This is especially critical in the hearts of giant galaxy clusters, the universe's most massive structures. Here, the density of gas is so immense that its natural cooling time should be incredibly short, leading to a torrent of new stars that we never observe. What stops it? The central black hole, through its periodic outbursts, heats the gas and raises its entropy, a measure of its disorder and heat content. High-entropy gas is stable, diffuse, and resistant to collapse. It is the black hole's way of placing the galactic fuel on a high shelf, out of reach of gravity's relentless pull. This decision-making process, happening to countless clouds across cosmic time, is the central theme that runs through every modern model of galaxy evolution. It is the invisible hand that guides a galaxy's trajectory from a chaotic youth to a stable maturity, ensuring the universe produces not monsters, but the beautiful diversity of galaxies we see today. The very chemistry of the cosmos is written by these dark hearts. Beyond simply controlling the growth of galaxies, supermassive black holes act as master chemists, stirring and distributing the fundamental elements of life itself. Inside stars and the fiery explosions of supernova, nuclear forges create heavy elements like carbon, oxygen, and iron. These metals, as astronomers call all elements heavier than hydrogen and helium, are the building blocks of planets and life. But how do these ingredients escape the crowded galactic core to enrich the wider universe? The answer lies in the same powerful outflows we have discussed. When a black hole erupts, its galactic winds do not just carry hot, pristine hydrogen. They sweep up this newly forged, metal-rich material from the central regions, carrying it on a colossal journey. These winds act like a cosmic conveyor belt, lifting enriched gas from the inner galaxy and hurling it high into the galactic halo, or even casting it out into the vast emptiness between galaxies. This process, called chemical enrichment, permanently pollutes the pristine gas reservoirs that exist in the galactic suburbs and beyond. The consequences are profound. This pollution changes the very nature of future star formation. Metal-rich gas cools far more efficiently than pure hydrogen and helium. The presence of these heavy elements allows the gas to radiate its heat away, making it easier for clouds to collapse and ignite into new stars. So, by seeding the outer reaches with metals, the black hole indirectly primes those regions for future stellar birth, but with a crucial caveat: the material is now different. The next generation of stars formed from this enriched gas will themselves be metal-rich, influencing the types of planets that can form around them. We can even see the black hole's chemical signature etched into the structure of galaxies themselves. In many systems, careful analysis reveals a distinct metallicity gradient. The abundance of heavy elements is highest near the galactic center, where the black hole's winds originate, and gradually decreases as you move outward toward the pristine galactic edges. This gradient is a direct fossil record of the black hole's stirring action, a lasting imprint of past outbursts. When astronomers point their spectroscopes at the light from distant quasars, they can detect the absorption lines of these same heavy elements in the intergalactic medium, far from any galaxy. This is the ultimate evidence of the black hole's reach, a testament to its role as a cosmic polluter, seeding the void with the very elements that make worlds like our own possible. This chemical dimension adds a deeper layer to the black hole's role, proving it is not just a destroyer or a regulator, but a fundamental agent in the complex cycle of cosmic ingredients. Without the tempering influence of its central black hole, a galaxy would face a cosmic crisis of its own making. This is the overcooling problem, a fundamental flaw in our early understanding of how galaxies evolve. In the pristine cold dark matter model, the process seems straightforward. Vast halos of dark matter pull in enormous amounts of ordinary gas through their immense gravity. This gas should then cool down with breathtaking efficiency, radiating away its heat and collapsing into a frenzy of new stars. The logical outcome is a universe filled with galaxies that are far too blue, too massive, and too rich with young stars. They would be cosmic gluttons devouring their fuel in a frantic burst of creation. Yet when we look at the real night sky, this is not what we see. We observe a calm and orderly distribution of galaxies, many of them red and quiescent, their star-forming days long behind them. For a long time, our best computer simulations could not explain this discrepancy. They produced a universe of monsters, galaxies that grew to unrealistic sizes and failed completely to reproduce the quiet giants we know exist. The models were missing a crucial ingredient, a cosmic thermostat that could turn down the heat of star formation. The introduction of active galactic nucleus feedback was the breakthrough that solved this decades-old puzzle. It provided the necessary source of heat to counteract the relentless pull of cooling. This is especially vital in the hearts of massive galaxy clusters, where the density of gas is so extreme that its natural cooling time should be incredibly short. Without a balancing force, these central galaxies should be the most prolific star factories in the universe, blazing with the light of billions of new stars. Instead, we find them quiet and red. The supermassive black hole solves this by injecting tremendous energy directly into this gas, raising its temperature and entropy. It effectively places the galactic fuel on a high shelf, out of reach of gravity's grasp. This single theoretical adjustment transformed our digital universes. Suddenly, the simulated galaxies began to look right. Their growth was tempered, their star formation rates declined realistically, and they settled into the same diverse population we observe. The overcooling problem revealed a profound truth, that the black hole is not an optional feature but a mandatory component. It is the critical regulator that prevents a cosmic imbalance, ensuring that galaxies do not burn too bright and die too young, but instead mature into the stable, long-lived structures that fill our cosmos. But what about the smallest galaxies in the cosmos? The story of black hole feedback takes a surprising turn when we look at dwarf galaxies. These are the cosmic minnows, small, faint collections of stars and gas that are the building blocks of larger galaxies. For a long time, it was assumed their black holes, if they had any at all, were too small and weak to matter. Yet recent observations have shattered that simple view. We now see clear signatures of active galactic nuclei in some dwarf galaxies, proof that even these modest systems can host a central engine. The question is, can such a small heart have a real voice? The energy output from a dwarf black hole is a tiny fraction of its supermassive cousins. Its outbursts are whispers compared to the cosmic shouts from a giant elliptical galaxy. This means its influence is far more localized. It cannot blow out gas on a galactic scale or quench star formation across the entire system. Its reach is limited to the very central regions. However, within that sphere, its power is very real. The outflows from a dwarf, a GN, while smaller, can still stir up the gas in the galactic core. They can heat the immediate environment and potentially drive small-scale winds. This localized feedback might not shut down the galaxy's star-forming ability, but it could regulate it in a different way. It might prevent a single, dense burst of stars from going supernova all at once in the center, which could itself blow out gas in a chaotic and disruptive way. Instead, the black hole provides a gentler, more continuous form of regulation, a subtle hand on the thermostat that maintains a steadier pace of stellar birth. This has fascinating implications for the chemical life of the dwarf galaxy. The outflows from its small black hole can still act as a local mixing agent, churning the metal-enriched gas from supernova and spreading it through the inner galaxy. This could create a more chemically homogeneous core, influencing the composition of the next generation of stars born there. Studying these small-scale systems is a critical test for our models. It forces us to ask if the rules of black hole galaxy co-evolution are universal. Do they scale down neatly, or does the physics change when gravity's grip is weaker? The evidence so far suggests that black holes can be important players even in the smallest of galaxies, but their role shifts from a dominant overlord to a local manager. This exploration of the cosmic underdogs reveals that black hole influence is not a privilege reserved for the most massive galaxies. It is a fundamental process that operates across the entire spectrum of galactic size, a universal dialogue between a dark heart and its stellar home. This ancient puzzle lies at the heart of galactic life itself. Did the galaxy build the black hole, or did the black hole's seed somehow dictate the galaxy's very birth? For a long time, astronomers wrestled with this cosmic chicken and egg scenario, a question that seems to have no simple beginning. The tight correlation between their masses is undeniable, a rule written into the fabric of the cosmos, but it does not tell us which one led the dance. The emerging answer is as complex as it is beautiful. They did not form in sequence, one after the other. Instead, the galaxy and its dark heart grew up together, their fates intertwined from the very start. Their growth was a shared history, a constant conversation where the black hole's feedback acted as the vital link that kept their masses in lockstep. Think of it not as a chain of cause and effect, but as a symbiotic relationship, like two trees growing so close that their roots and branches become one single, living structure. In the chaotic dawn of the universe, the first black holes may have sprung from unusually heavy seeds. These could have been the direct collapse of gigantic gas clouds, forming monsters with the mass of 100,000 suns from their very first breath. With such a massive head start, these primordial black holes could establish a powerful feedback loop almost immediately, their youthful outburst shaping the infant galaxy swirling around them from its earliest moments. Yet in other cosmic neighborhoods, the sequence might have been different. A galaxy could begin forming first, its stars igniting from collapsing gas. Then, a dramatic event like a galactic merger would act as a universal trigger. The chaotic gravitational forces of the collision would accomplish two things at once. They would funnel gas to the center to fuel a rapid growth spurt for the black hole, while simultaneously compressing gas clouds throughout the galaxy to spark intense waves of star formation. In this scenario, the galaxy and its core are not growing in a steady whisper, but in a shared, violent shout. This means there is no single answer that fits every galaxy we see. The precise story of their co-evolution, the exact timing of their growth spurts, is a unique signature for each system. Unraveling this requires us to become cosmic detectives, piecing together clues from across time. We look at the most distant quasars to see the rules being written in the early universe, and we study nearby galaxies to read the final chapter of their long story. We then feed all these clues into immense supercomputer simulations, running the clock forward over billions of years to see which initial conditions produce the universe we actually observe. This great co-evolution mystery remains one of the most compelling quests in all of science, a puzzle that pushes us to build ever more powerful telescopes and to dream of ever more elegant theories. The final shape of a galaxy is a direct signature of its black hole's past activity. Think of a spiral galaxy, its elegant arms spinning in a delicate balance. At its heart, a supermassive black hole is not merely a passenger, it is a cosmic architect actively sculpting the galactic landscape through its powerful feedback. One of its most profound effects is the creation of galaxies dominated by a central bulge. By unleashing torrents of energy that quench star formation in the inner regions, the black hole ensures that new stars cannot form efficiently in the disk. Over time, this suppression allows the older, redder stars in the central hub to dominate the galaxy's light and mass, gradually transforming a star-forming spiral into a smooth, bulge-dominated elliptical system. The violence of this process is etched into the galaxy's very gas. Powerful outflows and relativistic jets do not just heat the interstellar medium, they physically plow through it. These forces carve out colossal cavities and generate expanding shells of shocked material, like a stone thrown into a pond sending ripples across the water. This restructuring of the gas distribution alters the internal dynamics of the entire galaxy, redistributing angular momentum and preventing the smooth, rotating disk from reforming after a major disruption. Yet in a quieter, more stable galaxy, this same feedback can play a protective role. A moderate level of activity can prevent gas from cooling and collapsing into an overly dense central mass. Without this regulatory break, a runaway buildup of stars in the core would destabilize the entire disk, potentially destroying its delicate spiral structure. The black hole's gentle heating maintains the disk's stability, allowing it to persist for billions of years. The most dramatic morphological transformations are seen in the aftermath of galactic collisions. When two galaxies merge, the resulting chaos funnels a tsunami of gas toward the central black hole, igniting a brilliant quasar. The ensuing feedback acts as a cosmic pressure release valve. Its powerful winds blow away the loose gas, halting the starburst and helping the chaotic, merging system relax into a new, stable equilibrium, often as a smooth, featureless elliptical galaxy. This architectural role is undeniable. The supermassive black hole is not a silent tenant residing in the galactic core. It is the active designer of its home, its past outbursts forever frozen in the galaxy's final form. A galaxy's cosmic neighborhood dictates the very nature of its dark heart's influence. The environment a galaxy calls home, whether a crowded metropolis or a quiet rural expanse, sets the stage for how the supermassive black hole will wield its power. In the dense, bustling cores of galaxy clusters, the rules of engagement are dramatically different from those in the isolated void of the cosmic field. These clusters are cities of galaxies, swimming in a searing ocean of gas known as the intracluster medium. This gas is unimaginably hot, reaching temperatures of millions of degrees, and it represents a colossal reservoir of potential fuel. Left to its own devices, this gas should cool, flowing inward to feed the central galaxies in a torrential downpour of new stars, but that is not what we see. Instead, the central black hole acts as a cosmic furnace, its periodic outbursts pumping vast energy back into this gaseous ocean. The relativistic jets and winds from the active nucleus create immense bubbles and stir the intracluster medium, reheating it and preventing the catastrophic cooling flow. This delicate thermal balance is a direct result of black hole feedback, a self-regulating loop that keeps the cluster gas hot and the central galaxy from gorging itself on a stellar feast. We see this breathtakingly clear in famous clusters like Perseus, where the Chandra X-ray Observatory has mapped colossal cavities, ghostly reminders of past black hole eruptions, perfectly balancing the cooling radiation from the hot gas. The chaotic environment of a cluster also provides constant triggers for this activity. Frequent gravitational encounters and galactic mergers act as cosmic alarms, shaking loose gas and funneling it toward the central black hole, ensuring its feedback is a regular and powerful force. This is feedback operating at its most potent, a large-scale environmental manager maintaining order in a crowded urban cosmos. Now, journey to a field galaxy, a solitary island adrift in the vast, empty darkness between clusters. Here, the environment is profoundly quiet. There is no dense, hot intracluster medium to heat or regulate. The galaxy must rely almost entirely on its own internal gas reservoir. In this serene setting, the black hole's feedback takes on a different character. It is less about fighting off an external ocean of hot gas and more about managing the internal plumbing. Without the constant triggers from galactic neighbors, the black hole's activity is often less violent and explosive. Instead of dramatic, cluster-style outbursts, the feedback can be a more gentle, continuous process. Think of it as a low, steady hum of regulation rather than a periodic roar. The black hole may experience smaller, more frequent feeding events, releasing just enough energy to gently heat the surrounding gas halo, preventing it from cooling too quickly and collapsing into a sudden burst of stars. This moderates the galaxy's growth over immense timescales, allowing for a slow, sustainable evolution. It is the difference between a central furnace that blasts on occasionally to melt an ice age and a subtle thermostat that maintains a comfortable room temperature for billions of years. This profound environmental dependence reveals the incredible adaptability of black hole feedback. The same fundamental process, the conversion of gravitational energy into galactic-scale influence, is exquisitely tuned by the cosmic context. Whether in a dense cluster or the lonely field, the supermassive black hole listens to its surroundings, its powerful voice modulated by the emptiness or the crowd, forever sculpting its home in a dialogue with the cosmos itself. Astronomers piece together this cosmic story by listening to the universe in many different colors of light. Each wavelength reveals a separate chapter in the tale of black hole feedback. In the high-energy realm of X-rays, our most powerful observatories like Chandra peer into the hearts of galaxy clusters. They do not just see a uniform glow, they map colossal cavities, vast empty bubbles that have been punched into the searing hot gas. These are the ghostly imprints of relativistic jets, the lasting scars left by a black hole's ancient outburst. Surrounding these cavities, we can often detect faint, rippling shells of compressed gas, the shock fronts from that explosive energy release. This is feedback captured as a fossil record, a direct image of the black hole's physical impact on its environment. Meanwhile, radio telescopes chart a different aspect of the storm. They detect the faint, diffuse synchrotron radiation emitted by electrons spiraling at near light speed within the magnetic fields of those same jets. This radio glow traces the long-faded beams back to their source, outlining the architecture of the black hole's most powerful outbursts. But to understand what is being lost, we must look to the cold. Instruments like the Atacama Large Millimeter Array, or ALMA, scan the heavens in submillimeter and infrared light. They are exquisitely tuned to the faint thermal glow of cold molecular gas, the very raw material for stars. In galaxy after galaxy, ALMA has captured this cold gas not in tranquil clouds, but in turbulent, high-velocity outflows, being physically driven from the galactic core by the black hole's winds. We are watching the galaxy's future being stolen away. Through optical spectroscopy, we dissect the light from these active hearts. By splitting that light into a rainbow, we can read the fingerprints of different elements. The telltale sign of feedback is a Doppler shift, where the signature of ionized gas is stretched to redder or bluer wavelengths, indicating it is racing toward us or away from us at thousands of kilometers per second. This is how we measure the velocity of those immense galactic winds, quantifying the raw power of the expulsion. no single telescope can tell the whole story. The true breakthrough comes from multi-wavelength campaigns, where data from X-ray, radio, optical, and infrared observatories are combined like pieces of a puzzle. The X-rays show us the hot, shocked gas, the radio waves map the jet mechanics, the infrared reveals the warm dust, and the optical light details the ionized outflow. Together, they build a complete, multi-dimensional picture of the feedback process from its origin near the event horizon to its impact thousands of light-years away. To truly calibrate this engine, we need to know the mass of the black hole itself and how quickly it is feeding. This is where techniques like reverberation mapping come in. By monitoring the flickering light from the accretion disk and then measuring a time delay in the response of surrounding gas clouds, astronomers can effectively weigh the central monster and measure its accretion rate. These crucial parameters, the mass and the appetite of the black hole, are the fundamental dials that set the power of its feedback. The synergy of all these methods allows us to move from simply seeing that feedback happens to precisely calculating the immense energy and momentum it injects into galactic ecosystems. Our observational tools are constantly evolving, each new instrument sharpening our vision and deepening our understanding of this cosmic dialogue. The sheer power unleashed by a feeding black hole is almost beyond human comprehension. To grasp its true scale, we must calculate its energy budget to quantify the raw force it can wield over its galactic home. During its most luminous phases, a brilliant quasar can release up to 10 to the 46 ergs of energy every single second. To put that number in perspective, that single object smaller than our solar system can outshine an entire galaxy of hundreds of billions of stars for millions of years. This staggering output is born from the phenomenal efficiency of the accretion process itself. For a maximally spinning black hole, the conversion of infalling matter into pure energy can reach an astonishing 40% efficiency. Compare that to the nuclear fusion powering our Sun, which converts less than 1% of its mass into energy. The black hole's engine is, by a vast margin, the most efficient and powerful energy source known in the entire universe. This is not a gentle glow, it is a cosmic firestorm of radiation. But light is only part of the story. This titanic energy is deposited into the galaxy's gas in three distinct ways. First, there is the relentless radiation pressure, a torrent of photons that physically pushes on gas and dust. Then, there is the mechanical work done by the relativistic jets, colossal pistons of plasma that ram into the interstellar medium. Finally, there is straightforward thermal heating, where the energy simply cooks the gas, making it expand violently. The critical question is whether this power is sufficient for the task at hand. When we calculate the gravitational binding energy, the force needed to hold a galaxy together, and compare it to the energy required to lift gas out of its deep gravitational well and expel it, the answer is resoundingly clear. A single, sustained outburst from an active supermassive black hole can release more than enough energy to unbind the entire galaxy's gas reservoir. The raw power is undeniably there. The true key to the mystery, however, lies not in the total energy produced, but in the feedback efficiency. This is the crucial fraction that determines how much of the black hole's raw output actually couples to and influences the surrounding gas. If the efficiency is too low, the energy simply escapes into space as wasted light, leaving the galaxy untouched. If it is too high, the outburst could be catastrophically destructive, tearing the galaxy apart entirely. Modern astrophysical models suggest that only a few % of the total energy needs to be efficiently transferred to the gas to produce the large-scale winds and quenching we observe. This delicate efficiency parameter is what allows the black hole to act as a precise regulator rather than a mere bomb. It transforms an almost unimaginable release of power into a controlled, sculpting force. The energy budget does not just suggest that black holes can influence their galaxies. It proves they have more than enough power to be the dominant architects of galactic destiny, cosmic engines whose brief but brilliant outbursts write the rules for an entire universe of stars. Rotation transforms a black hole from a passive trap into a dynamic engine. While its mass dictates its gravitational pull, it is the black hole's spin that determines the efficiency and character of its galactic feedback. A rapidly rotating black hole drags the very fabric of space-time around with it, creating a vortex of energy just outside the event horizon. This rotational energy is not locked away. It can be tapped through a remarkable mechanism known as the Blandford-Zeenagic process. Here, intensely wound magnetic fields act like a cosmic turbine, extracting the black hole's spin energy and channeling it into the formation of incredibly powerful and focused relativistic jets. A high-spin black hole does not just produce jets, it produces torrents of plasma moving at a greater fraction of light speed, carrying far more energy and momentum into the galactic environment. These supercharged jets are far more effective at their work. They plunge deeper into the surrounding gas, carving larger cavities and driving stronger shock waves that heat the interstellar medium more violently. The spin's direction also plays a crucial role. If the black hole's rotation axis is misaligned with the galactic disk, its jets will blast directly through the plane of the galaxy, ensuring their energy is dumped efficiently into the densest star-forming regions. If the axes are aligned, the jets might simply drill out into the emptiness above and below the galactic plane, their energy having a more limited impact. Measuring this vital property is a monumental challenge, but astronomers have a clever tool. Using X-ray spectroscopy, they can probe the very inner edge of the accretion disk, a region where the intense gravity of a spinning black hole distorts the fabric of space. By analyzing the specific distortion of X-ray light emitted from this hot, inner maelstrom, scientists can estimate the black hole's spin. A black hole's rotational history is written by its past. Major galactic mergers can send gas pouring in from random directions, chaotically spinning up the central monster. In contrast, a steady, ordered diet of gas from a consistent direction can also affect its rotation over billions of years. This means two black holes with identical masses can have vastly different spins, leading to completely different feedback legacies for their host galaxies. One might be a quiet neighbor, while the other, with its high spin, becomes an aggressive sculptor capable of launching jets that regulate star formation across vast distances. This reveals that the black hole's rotational energy is a colossal hidden reservoir, a power source beyond mere accretion that can be unleashed to shape galactic destiny. The spin of a supermassive black hole is not a minor detail. It is a fundamental control dial for the entire galaxy, adding a profound layer of nuance to the cosmic dialogue between a dark heart and its stellar home. These galactic regulators are not eternal. The brilliant cycle of feedback that sculpts galaxies is a spectacular but fleeting phase in the life of the cosmos. As we project the universe's future across trillions of years, we see a story of slow, inexorable fading. The primary fuel for this cosmic engine, cold hydrogen gas, will eventually be consumed, ejected, or locked away in the corpses of dead stars. Star formation will sputter and cease across the entire universe. The brilliant spiral arms of galaxies like our own will dim, their blue light extinguished as the last massive stars explode and fade. What remains will be a galaxy of red dwarfs, white dwarfs, and neutron stars, a gradually darkening stellar graveyard. In the heart of this darkness, the supermassive black hole will still reside, but its voice will have fallen silent. With no gas left to accrete, the cycle of feedback will be broken. The brilliant outbursts of radiation, the powerful jets, the hurricane-force winds, all of it will come to an end. The black hole will become a truly dark sentinel, a gravitational monument to a bygone era of cosmic construction. Its immense mass will still govern the orbits of the surrounding dead stars, but it will no longer shape their creation. It is a dormant king ruling over a kingdom of ghosts. Yet even in this profound quiet, there may be brief, final acts. Over almost unimaginable timescales, the slow gravitational dance of dark matter will continue to pull galaxies together. In the far, far future, two such stellar graveyards might still merge. This final, slow-motion collision could, for a fleeting moment, stir the last vestiges of interstellar material, or even disrupt the orbits of old stars, sending a tiny trickle of matter toward the waiting central giants. This could ignite one last, faint flicker of activity, a ghost of a quasar shining in the profound darkness, but it would be a temporary resurrection. The universe's expansion will ultimately seal this fate. As space continues to stretch and cool, driving galaxies apart, even these rare merger events will cease. The supermassive black holes will then face their own ultimate fate, a process so slow it defies human comprehension. Through Hawking radiation, a black hole gradually loses mass, emitting a faint whisper of particles. For a supermassive black hole, this evaporation time is longer than the current age of the universe by a factor of trillions upon trillions. In a practical sense, they are nearly permanent fixtures. Yet in the theoretical end, during the era of the heat death, even these dark titans will, over an infinite timeline, radiate away into nothing. This cosmic perspective frames the vibrant feedback we see today as a brilliant, transient fire in the long, cold night of cosmic history. It is the dynamic, middle chapter of a story that begins in a blaze of light and ends in the quietest dark, reminding us that the powerful dialogue between a black hole and its galaxy is a precious and passing phase. Even with all we have uncovered, profound mysteries remain at the very frontier of our knowledge. How did the first supermassive black holes grow so immense when the universe was still in its infancy? The detailed physics of how accretion disks form and how magnetic fields launch relativistic jets is still being decoded in supercomputer models. Perhaps the most critical unknown is the exact coupling efficiency, the precise mechanism that allows a fraction of the black hole's raw energy to so effectively heat and expel galactic gas. The tools to answer these questions are already pointing toward the heavens. The James Webb Space Telescope peers back to the epoch of the first galaxies and quasars, seeking the seeds of these cosmic regulators. The upcoming square-kilometer array will map the faint radio glow of hydrogen gas with exquisite detail, tracing how black hole winds reshape entire galaxies. And the Gravitational Wave Observatory, LISA, will listen for the low-frequency hum of merging supermassive black holes, revealing their growth through cosmic collisions. On the theoretical front, the grand challenge is to bridge the staggering gap in scale. Scientists are striving to integrate the complex, small-scale physics occurring just outside the event horizon with the large-scale evolution of a galaxy spanning hundreds of thousands of light-years. Our simulations are becoming more sophisticated, but the sheer diversity of active galactic nuclei presents a puzzle. A brilliant quasar, a radio galaxy with colossal jets, and a modest Seyfert galaxy may all represent different facets of the same feedback process, operating at different strengths or in different galactic environments. This suggests that feedback is not a single, uniform force, but a versatile toolkit whose instruments are used differently from one galaxy to the next. Beyond individual galaxies, a grander question looms. What is the role of supermassive black holes in weaving the cosmic web itself? Their powerful outflows can enrich the vast intergalactic medium with heavy elements and heat entire galaxy clusters, potentially influencing the flow of gas along dark matter filaments and guiding where future galaxies will form. These open questions are not a sign of failure, but a map of our curiosity. They ensure that the study of black hole feedback remains a vibrant, living field, forever on the cusp of the next revolutionary discovery that will rewrite our understanding of the cosmos. This cosmic regulation touches a deeply personal question. Could a universe without supermassive black holes ever have given rise to life like us? Picture a cosmos where these dark regulators never formed, where the galactic feedback loop was broken from the start. In such a reality, galaxies would be free to gorge on their gas reserves, igniting stars in a frantic, runaway explosion of creation. They would swell into monstrously oversized giants, their brilliant but short lives dominated by furious starbirth. The stellar populations in this alternative universe would look entirely different, skewed toward massive, hot, blue stars that burn furiously and die young in supernova explosions. This chaotic, accelerated life cycle would dramatically alter the chemical landscape. While supernova would still forge heavy elements, the distribution of these metals would be a chaotic mess. The gentle, widespread enrichment provided by black hole outflows, which steadily seed galactic halos with life's building blocks, would be absent. The cosmic conveyor belt that distributes carbon, oxygen, and iron far from the violent galactic core would be broken. Planetary systems might still form, but they would likely be concentrated in tumultuous central regions, bathed in deadly radiation from frequent supernova. The quiet, habitable suburbs of spiral arms, like the one our own solar system occupies, might be exceedingly rare or never form at all. The very availability of rocky planets could be compromised, as the precise metallicity needed to form terrestrial worlds might not be consistently achieved across the galaxy. The intergalactic medium itself would be different, a more pristine and unpolluted sea, lacking the heavy elements that black hole winds hurl into the void. This speculative journey reveals a profound and humbling possibility. The same forces that quench galaxies and dictate their shape may also be responsible for creating the stable, chemically rich environments where life can eventually emerge. The supermassive black hole is not merely a destroyer or a regulator, but a cosmic gardener, taming the wild growth of stars to cultivate a universe capable of complexity and perhaps consciousness. Our own existence may be an indirect yet remarkable consequence of the dark hearts that beat at the center of galaxies. This grand narrative reveals a universe governed by a delicate balance, where the most destructive forces are also the architects of cosmic order. The supermassive black hole, with its explosive jets, silent radiative tides, and galactic winds, functions as a master regulator, a fundamental component in the galactic machinery. Its role is not one of mindless destruction, but of precise and necessary control. The intricate dance between its feeding cycles and the galaxy's star formation ensures a sustainable evolution, a cosmic check on what would otherwise be a runaway frenzy of stellar birth. The profound correlation between a black hole's mass and its galaxy's central bulge is no mere coincidence. It is the indelible signature of this deep, co-evolutionary relationship, a partnership forged and refined over billions of years. The next time you gaze at the night sky, let your perspective shift. See beyond the scattered points of light to the invisible hands that sculpt them. Recognize the quiet, dark hearts beating at the center of galaxies, whose powerful feedback loops have written the rules for cosmic structure and stability. This story of how black holes control galaxies stands as one of the great triumphs of modern astrophysics, a beautiful testament to the dynamic and profoundly interconnected nature of our existence. We would love to hear which part of this cosmic dialogue fascinated you most. Share your thoughts and questions in the comments below, and subscribe to continue exploring the deepest mysteries of space with us.